Hi everyone, I'm Ch8. Welcome to the tutorial on relations. Before we begin, let us recall some of the definitions from the lecture. Definition 1. Let A and B be sets. A binary relation R from A to B is a subset of A cross B. Okay, we can also write in this manner. R is a subset of A cross B. And we say that X is related to Y by R, okay, which is X. So in this case here, we can write either XRY or XY is in R, where X is from A and Y is from B. Okay, note that the orders of where does this element come from is important. Okay, similarly, we can define the inverse relations R inverse, which is instead from A to B, now we from B to A. Okay, it's defined in such a way that R inverse is the collections of all elements from R. However, this time around we switch the positions. Okay, next, definition 3. Okay, now we suppose both set A and B are finite sets. And then we write elements of A in the following: A1, A2, all the way until AN. And B start from B1 all the way until Bn. Okay, let E be an M by N matrix. And we define the entry of E as follows. So Eij, okay, is equals to true if Aibj is an element in R. Else is equals to false. In other words, it means that if Aibj is not an element in R, then Eij, entry of Eij is equals to false. Okay. Now, we define another set, C, also a finite set, and then we say that it's a collection of elements C1 all the way until CL. Now, we consider another binary relation S from B to C. Then the composition of R and S is a relation from A to C, which is defined as follows. So in this case here, you can see that if AICK is an element in C, A cross C, this implies that there exists some BJ in B such that we have AIBJ is in R and BJCK is in S. With this in mind, now we can tackle question 1 to 4 in the tutorial. Question 1. Consider the set A is a collection of element 1 and 2, B, 1, 2, 3. Okay. We define the relation as follows. XY is in R if and only if X minus Y is even. Now our task here is to find R inverse and its matrix representations. First, let us see what is the element in R. So R means that for any element in R, okay, then if we have XY is in R, recall that XY is in R, then X minus Y must be even. So in this case here, we can easily verify that 1, 1, 1, 3, and 2, 2, right? They are an element in R. Then by definition, R inverse means that we switch the positions. We will have R inverse is equals to 1, 1, 3, 1, and 2, 2. Now, we let E and G be its matrix representation of R and R inverse respectively. Okay. Then by definition of matrix representations, it means that we can write E is equals to the following: true, false, true. The second row will be false, true, false. Okay. So we can just see from one small example, which is here. You can see this is true because we have A1, B1, right? Where this system for A1, A1, A2, B1, B2, B3. Okay, so you can see each of the entries correspond to one of the element here, B3. Okay, A2, B1, similarly A2, B2, and A2, B3. Okay, and then based on this, E, find this element here. See, R has 3 elements. So in this case here, we have 3 true. Okay. Okay. Then we know that R inverse, okay, is the transpose. The matrix for R inverse is a transpose of E. In other words, we can say that G is equals to E transpose. So what we do here is, since we are tasked to find the matrix representation for R inverse, we just need to transpose the matrix E. this is equals to E transpose. Okay. Now question 2, we also given two sets, A which is 2, 3, 4, B 2, 6, 8, and the relation is defined as if we have x, y is in R, if and only if x divides y. In other words, we can say that y is a multiple of x. And now we are tasked to find the matrix representations for R inverse. Okay. First, we can easily verify that R is equals to this set of elements, which is 2, 2, 2, 6, 2, 8, 3, 6, and 4, 8. Okay. By definition of R inverse, we just need to switch the position of the element in R. Okay. Then now, let G be the matrix representation of R inverse. Okay. Then we have G is equal, can be written as follows. True, false. Okay, in other words, you can see that this is another way to view it is we can see that the comment below. If Gij is equals to true, okay, then it means that Bi must be a multiple of Aj. Right? Let us randomly take one to verify. In this case here, this corresponds to B2 A2, right? So in this case here, if we list the elements, okay, every element we list it in order. Okay, we can see that indeed 6 is a multiple of 3 because 6 is equals to 2 times 3. Okay, now question 3. Question 3 is about proving. So consider a relation R from Z to Z, means that a set to itself, right, is defined by x, y is in R if and only if 2 divides x minus y. Then what we want to do is we show that if n is odd, then n is related to 1. In other words, we want to say that n, okay, and 1 is in R. Okay, proof. For this, I will prove by contradictions. Suppose not. We suppose n is odd and n is not related to 1. Since n is not related to 1, we can write as follows. N1 is not an element in R. Okay, since N1 is not an element in R, this implies that N minus 1 is not divisible by 2. This is how I arrive. And then since N minus 1 is not divisible by 2, then N minus 1 must be an odd integer, which means that N minus 1 is congruent to 1 modulo 2. And next, since modulo is closed under additions, then we can plus 1 on both sides to get N is congruent to 0 modulo 2. This implies that N must be an even number. Hey, this contradicts, right, to our assumption that suppose we have N is odd and then N is not related to 1. So here I'm telling you that if we have N is not related to 1, slowly derive all the way, we will have another conclusion, which is N is even. This is the contradictions, right? You can see. Because it's impossible for us to have N is even and odd at the same time. So we can say that the hypothesis is correct, which is N, 1 is an element in R. Question 4. Consider the sets. A is a collection of elements A1, A2, B, B1, B2, C is C1, C2, C3. Okay, with the relations, R means that from A to B and S is from B to C as follows. So R have 2 elements, right? A1, B1, A1, B2. Similarly, S, we have 4 elements. Okay, then we are asking, what is the element? Okay, what is the matrix for S composite with R? In this case here, answer. Okay, in this case, I feel that it's easier to draw a diagram and then we demonstrate how can we get the solutions from here. So so here you can see, because R is a relation from A to B, so in between we have R, and then here we have S. Right? Let me change color for easier identifications. So since we have A1, B1 means that A1 is connected to B1. Similarly, A1 is connected to B2 as well. Then we have B1, C1. So B1, maybe I change the other color. How about blue? Sorry, green. Okay, maybe switch to green. B1C, B2C1, B1C3, and then B2C2. Okay. Now, let E be matrix for S compose R. Then we can write E as follows. So you can see that for each of the elements here, because this is a 2 by 3, this is a 2 by 3 matrix. Right, let me change color again. Then in this case here, we will see that the first one corresponds to A1, C1. Second one is A1, C2. Third one is correspond to A1, C3. So first, we can see from A1 to C1, there exists a path, right? Which means that you see, we can go from A1 to B1 and B1 to C1. So true. Similarly, A1 to C2, we also can find a path, right? So we can have A1 to B2, then B2 to C2, true. As long as there exists a path, then we are fine. Okay, then last one, A1, C3. So we can, so A1, C3 means that we can go from A1 to B1 and B1 to C3. True. Okay. Then A2. As you can see, there are no line attached to A2, which means that we can easily just say that they are all false. For A2, C2, this is the entry correspond to A2, C2. This entries correspond to A2, sorry, this is A2, C1, A2, C2, and A2, C3. They're just false. Okay, all these we just purely follow the definitions. And question 4.2. In general, what is the matrix of S compose R? So by definition again, we know that S compose R means that it's the collection of all elements. Okay, if there exists a B that can connect these two elements together, means that okay, you can easily see that it means that suppose we have three sets A, B, and C, right? Then in this case, as long as, so this is a relation R, this is relation S. So as long as there exists, you take any two elements from A, okay, any one element from A and any one element from C. If you can find one B such that it connects A, connects them together, means that they are an element in R, and then you can find another line which is an element in S. Okay, then this implies that we can directly join them together. Okay, then if we write in terms of matrix, let E be a matrix for S compose R, then we know that EIK is true if AICK is in S compose R, else it is false if AICK is not in S compose R, right? Furthermore, we can see that E is a cardinality of A by cardinality of C matrix. Okay, now let's introduce more definitions from the lecture notes. We say that a relation R on a set A is reflexive if every element on A is related to itself. So this is the math notation for X in A, X, comma, X is in R. Or you can also write XRX. Okay. Then we say that a relation on a set A is symmetric if you have X, comma, Y is in R, implies that Y, comma, X is in R. Similarly, we have transitive if you have X, Y is in R and YZ is in R, implies that XZ must be in R. Okay. When all these three achieve, which means that if 5, 6, 7 achieve, then we say that R is an equivalence relation. So in this case here, usually definition works in if and only if directions. So therefore, if you see, we say that R is an equivalence relation, this implies that R satisfies the three properties, which is R is reflexive, symmetric, and transitive. And then if I tell you that R is reflexive, symmetric, and transitive, then we know that R is of equivalence relation. Okay. Then after that, we define equivalent class. A in A means that A is an element in the big A, okay, as follow. Okay, means that any element that has a relation with A, okay, we collect them. So in case here, you can see that this class of A is a subset of A. Yeah, it's a subset because it's a collection of elements from A, because all these X are not is from A, and this A is also an element A. So it's a collection of elements of A. Okay, so it's a subset of A. Can then the next we say that a relation, okay, R on a set A is anti-symmetric. Anti-symmetric. Okay, if we have XY is in R and YX is in R, implies that X must be equals to Y. Okay, so now we say that R, let R be a relation on a set A, then we say that R is partial order on A if R is reflexive, anti-symmetric, and transitive. Note that the common conditions for A between partial order and equivalence relation is that reflexive and transitive remains. Okay, but for equivalence we have symmetric, and partial order we have anti-symmetric. Okay. Then definition 12, which is the last definition in our lecture, which is let A be a set and R is be a binary relation on A, then the transitive closure of R, okay, is the binary relations RT on A satisfying three properties. First, RT is transitive, okay? And the relation R is a subset of RT. And lastly, if S is any other transitive relations that contain R, then RT is a subset of S. In this way, you can also see that this means that RT, okay, is the smallest. This definition tells us that RT is the smallest set that contain R as its subset. Smallest is the smallest set, because this is saying that if you can find any other set, okay, S that contain R, okay, this implies that RT must also be the subset of S. So this here is guaranteed that RT is the smallest set that contains R. Okay, now let us shift on to question 5 of tutorial. Let R be a relations on Z, okay, set of integers numbers given by AB is in R implies that N divides AB. Okay, question now we are going to ask is R symmetric? Okay, proof. Let A be in R, okay, because we want to prove symmetric, this implies that we want to show that BA is also an element in R, right? So here, since AB is in R, then we can write, because of these relations here, AB is in R, then we can write AB is equals to NK for some integers K. Then in this case, if we multiply -1 on both sides, we will get the following. B minus A is equals to -NK. So this is, we can also write this as N times -K. -K is also an element in the set of integers, right? Therefore, we also have BA is an element in R. Conclusions, we have R is symmetric. Question 6. Let R be relation on a set A. Show that R is symmetric if and only if R is equals to R inverse. So let us prove these directions. Okay. Suppose R is symmetric. Then we take any element XY is in R. Right? Since R is symmetric, then we know that YX is also an element in R. This is what we know. Okay. Then by definition of R inverse, because we have XY is in R, right? Then of course we must have Yx is in R inverse. This is just purely by definitions, right? But don't forget, we also have Yx is in R, right? So if we, by definition of R inverse, we also have xy is in R. So no matter what element you take from R, okay, it will also appear in R inverse. Since this is true for all xy is in R, of course we can say that R is equals to R inverse. Okay, the other directions. Now we suppose R is equals to R inverse. Then we take any element x, y is in R, because we want to show that R is symmetric. This implies that we want to show that Yx is also an element in R, right? This is what we want to show. And since R is equals to R inverse, then we can say that from the last week set theory, we know that R inverse is a subset of R, right? If we have xy is in R, by definition, we will also have Yx is in R inverse, right? By definitions, we know that since xy is in R, then we also can get, this implies that Yx is in R inverse, right? R inverse, sorry. Yeah. But then we know that from here, you see R inverse is a subset of R. Therefore, we can conclude that Yx is also in R. Then we are done. So in this case, we conclude that R is symmetric. Question 7. Now we suppose the set A is a collection of elements A, B, C, D, and the relation of the element is R is given as below. So we have AA, AB, AD, BA, BB, CC, DA, DD. Then question, is this relation reflexive? Then we say that it must be it's reflexive because we can find AA. Every element reflects itself, right? So you have AA, BB, CC, DD, 4 elements. Then symmetric, it means that if you have AB, see, AB, if you have AB as an element, then we say that BA is also inside. So if you have AD, let me change the other color. AD, okay, AD, this implies that DA will be also inside, right? Then, is there anything else? No. And then we know that AA, because if you stick positions, it's still the same, it's still symmetric, right? Therefore, R is symmetric since we have all these elements inside. However, we can see that R is not transitive, because if R is not transitive, right, so it's sufficient for us to just give one counter example. Then you can see that you have BA is inside this element, and you have AD is an element in R. However, because of transitive, we should have BD is also an element in R. Here in this set here, we are, let me see, in this yellow color, we use yellow color, you see the set R, we can't find any element. BD is not in R. We cannot find any element inside. Therefore, R is not transitive. Okay, now we are asked to find the set A consisting of elements 0, 1, and 2, and the relation 0, 2, 1, 2, and 2, 0. Then we are asking, is R anti-symmetric, right? But here we can immediately see that it's no, because you have 0, 2, and 2, 0 is an element. Okay, they are an element in R. However, 2 and 2 is not equals to 0. Therefore, R is not anti-symmetric. Recall from the definitions. Let me try to link back. Right? Anti-symmetric means that if you have xy is in R and yx is in R, point 10. Okay? Definition 10. Then you must have x equals to y. However, this is not the case, right? We can see that 0, 2 and 2, 0 are in R, but 0 is not equal to 2. Therefore, R is not anti-symmetric. Okay, then the other one, we are asking, are symmetry and anti-symmetry mutually exclusive? Means that they can't be happening at the same time? No. The answer is no. Okay. Of course, when this answer is no, we just need to give one counter example. So let A be a singleton. Say, for example, any singleton you can think of. So let me, in my example, I just put A is equals to the set consisting of one element, which is 1. Okay. Let R be a relation on A such that xy is in R implies that x minus y is equals to 0, right? Then in this case, you can see that my R is only the cardinality. My R is also consisting of one set of element, which is 1, 1. That element with one. My R is a set with only one element, which is 1, 1. Then you can see that it must be symmetric. Sorry, you can see that this must be symmetric, right? Because x is equals to 1 and y is equals to 1. You can see that x is equals to 1. Sorry, let me write down first. Okay, because in this case, this implies that my x is equals to 1 and y is equals to 1. So, of course, x 1, 1 is inside R. That's for sure, right? And similarly, if you switch the positions, which is x minus y and y minus x, they are the same because since both of them are equals to 1. Then we also know that by anti-symmetric, this means that if we have 1, 1 is in R and 1, 1 is in R, because this is x, this is y, here this is y, this is x, right? Then we must have x is equals to y, which is obvious. 1 is equals to 1. Therefore, it's possible. They are not mutually exclusive. Okay, for question 10, we consider the relations given by divisibility on positive integers. That is, if you have xy is an element in R, if and only if x divides y. Okay, then we are asking, is this type of relations reflexive, symmetric, anti-symmetric, or transitive? Okay, first, we see that R is reflexive because you take any elements, x is in a set of positive number, right? So it's z plus. Okay, the notation is, then you can write x is equals to 1 times x because x divides x. Therefore, x is an element in R. Done. Reflexive. However, it's not symmetric. Why? Since in this case here, we just need to give one counter example. If you take 2 and 4, x equals to 2 and y equals to 4, then we know that 2, 4 is an element in R because 2 divides 4. But 4 does not divide 2, right? Because we can say that this is the same as if 4 divides 2, then implies that 2 is equals to 4 times half. This half is not an element in the set of integers. So this is impossible. Okay. Then R is anti-symmetric. So we try to test, we can test it. So take any element x and y from a set of positive integers, and then we suppose x comma y is in R and y comma x is in R, right? Then in this case, because you can also see that actually this one, some people might not find x divides y clear, so you can just write, because this is the same as saying if and only if. Yeah, you can also write in this way, y is equals to xz for some integers z. That's all. Yeah, that's the reason why you see half is not an integer. Sorry, I write wrongly. Okay. Let me rewrite everything. Z, right? Z is in Z, the set of integers. Z here. Very ugly. Okay. Okay. Right? So you see, this half is not an element in the set of integer, therefore fail. This one failed. So R is not symmetric. Then, okay, now let us go back to the anti-symmetric. We have xy is in R, right? So we can write that y is equals to xz1 and x is equals to yz2 for some positive integers z1, z2. Then we can sub, because x is equal to yz2, so we sub this one here inside to get y is equals to yz2 z1. Implies that z1 is equals to z2 z1. Then we note that because all of them are positive sign, positive integer, therefore my z1 z2 must also from positive integers, must be some elements in positive integers. So in this case here, we can conclude that z1 is equals to z2 because positive, right? Therefore, x is equals to y. Okay, then in this case here, we know that R is anti-symmetric. How about transitive? Transitive means that we take any element x, y, z is in z plus. Okay, then we suppose that x, y is an element in R, and then y, z is an element in R. Then by definitions, we will have, let me change the other color. By definition, we will have the following, right? Then similarly, we can sub this into this y here. Yeah, sub into this y here. Then we will have z is equals to x z1, z2, right? Since z1, z2 are integers, then the multiplication of these two must be an integer as well. Therefore, we have x divides z. Thus, we have xz is an element in R. Then we are done. Right? Then the next question is asking, what if R is defined over non-zero integers? Means that negative integers can be included as well. Then in this case here, we will know that R is not anti-symmetric. Why? Because just need to give counter example that x is equals to 2 and y is equal to negative 2. Then we know that xy and yx must be an element in R, because yes, you can see from the relations here. Okay, 2 is equals to negative 1 times negative 2, and negative 2 is equals to negative 1 times positive 2. Right? Then in this case here, 2 is not equal to negative 2, which is wrong. However, you can also, the next thing is you can verify that R is still reflexive, the star, through the method of proving them is the same. So R is reflexive and R is transitive, okay, which follow the similar arguments as star and star star respectively. Okay, question 11. Consider the set A run from 0 all the way to 8. Then we want to show that the relation R, okay, xy is an element in R if and only if 2 divides x minus y is an equivalence relation. So in this case, we have to prove that R is reflexive, symmetric, and transitive. First, we show that R is reflexive. Since for every element in A, we know that the element minus itself is equal to 0. And clearly, 2 divides 0. Therefore, x is an element in R. Okay, R is symmetric. So we take any element x and y from A, and we suppose that x comma y is an element in R. Okay, then by the definition of relations, we know that 2 divides x minus y. So we can write x minus y is equal to 2k for some integers k. Then in this case here, it's the same as saying we just multiply both sides by negative 1. Multiply negative 1, multiply negative 1, multiply negative 1 to get the following, right? Then we will have y minus x is equals to 2 times negative k. This implies that 2 divides y minus x, which means that y comma x is an element in R. Done. The R is transitive. So let x, y, z be any element in A. Then we suppose that x, y is an element in R and y, z is an element in R. This implies that x minus y is equals to 2k and y minus 2k1, and y minus z is equals to 2k2 for some integers k1, k2. Then we can see that we have the following. See that this is equals to y is equals to x minus 2k1, right? So we put here this into this equation here, y equals to 2k1 to get the following. Let me use red color. This is my y. Therefore, we have x minus z is equals to 2 times k1 plus k2. Which means that 2 divides x minus z. This implies that x is an element in R. Since we have proved that R is reflexive, symmetric, and transitive, then we know that R is an equivalence relation. Okay, now let us proceed on to question 12. I would say that question 12 is the most difficult tutorial questions for this tutorial. Okay, because the proving of this is not that easy. Okay, show that given a set A, an equivalence relation R on A, then we want to show that the equivalent classes of R partition A. Okay, proof. So first, let us put A1, A2 all the way, because the partition equivalent class, right, can be infinite. So in this case here, we cannot put a finite AN. For example, like A1, A2, all the way until AN. This we can only do this when we know that equivalent class is finite. However, here I'm just telling you that we have given a set A, we don't know whether the equivalent class of A is finite or infinite. So in this case here, we assume that it's infinite. So let A1, A2, A3, all the way be equivalent classes of A. Okay, then we want to show that all these equivalent classes that partition A. In other words, we want to show 2 points. First, we want to show that union, okay, of all these sets is equals to A. And second, we want to show that the intersection of any two distinct equivalent classes, okay, is NT. Okay, let's show point 1 first. Right, since this is equal, we want to show equal. So one of the best way if we try to show that it's a subset of each other. Okay, so let X be an element, okay, from the union of all equivalent classes. Then X is definitely an element in AJ for some J. Okay, then by definition of equivalent classes, recall the equivalent classes, they are actually subset of A, right? Each equivalent classes, they are subset of A. Therefore, X is also an element in A. Now, with this, we have proved that union of all the subset, okay, of all the equivalent classes, they are actually the subset of A. Okay, now then we work for the other way around, the other incursions. Usually in this direction, the other one direction. Usually when you prove 2 directions, one of them will be easy, the other one will be slightly more difficult. Okay, so let X be an element in A. Okay, since R is of equivalence relations, then of course you know that we must have X, comma X is an element in R, because R is equivalent. In here we have to make use of the assumption that R is equivalence relations. Therefore, X, okay, we do have, in this case here, we do have an equivalent classes that is negative of X. Okay, since X is an equivalent class, then this class must be equals to AJ for some J, because you see that, let me write in blue color. You see that here we consider all equivalent classes of A. Then this X here is one of the equivalent classes of A, right? So in this case here, of course, this AJ must be inside one of them. So this proves that A is a subset of the union of equivalent classes. Since we have both subset, they force it to be the same, which means that A is equals to union of I equals to 1 AI, where each AI, they are equivalent classes of A. Okay, with this, we're done with the point 1. Second, we want to show that the intersection of any two distinct class is NT. So now let AJ and AK be two distinct equivalence classes. Then AJ is equals to AJ and AK is equals to small ak for some elements, right? AJ and AK. Okay. Then we assume that there is one element okay, that live in both of these equivalent classes. Okay. Then we know that A is an element in AJ, and then by definition of Z, we know that A is also an element in AK. Since R is equivalence relations, then we know that AR, AJ, and AR, AK. If and only if we have the following: AJ, RA, and AR, AK. Since equivalence relations, we have reflexive, transitive, and symmetric. In this case here, we are trying to use transitive to get AJ, AK, which means that AK is subset of AJ. In similar way, we can also do the following. Observe here. We can also, because R is equivalence relation, we also achieve the following: AR, AJ, and we apply symmetric on this, on the second one, which is AKRA. Right? Then we use transitive to achieve that this one, to achieve that transitive because equivalence relation, we will have AKRAJ, which implies that AJ, the classes, the concurrent class AJ is a subset of AK in similar way, right? See, since you see in this case here, we can get AK is a subset of AJ and AJ is a subset of AK. Since I'm running out of space, let me define in this way. So it's the same, the idea is the same just now, which is in similar way, we can also get AJ is a subset of AK. Since we have AK is a subset of AJ and AJ is a subset of AK, then we will have AJ is equals to AK. So this is saying that if there's an element, okay, live in between these two classes, then this we will be forcing these two classes to be the same set, okay, exactly the same. Okay. Otherwise, the intersection is empty. Okay, in this way, this concludes the proof for the following, means which is that the equivalent classes of R partition A. Okay, question 13, which is the last question for this tutorial. Consider the set A, 2, 3, 4, 5, all the way until 10, and the relations X, Y is in R if and only if there exists Z integers such that Y is equals to CX. Then is R an equivalence relations? Is R a partial order? Okay, first we look at reflexive. Yeah, you realize that here I put it in integers, positive set of positive integers numbers. We can see that here you can see that A, okay, is a subset of C plus. So by proving, okay, all this, if this is true for Z plus, then it will be true for A as well. Because if this is true for Z plus, means that every element will fix into the conditions. Of course, A, every element in A is also an element in Z plus, which is set of positive integer. Of course, they will fix well into this type of relations. Okay, first we see that R is reflexive. Then for all X positive integers, we have X is equals to 1 times X, which implies that X, comma X is an element in R. Done. We have reflexive. Usually reflexive is the easiest to prove, then followed by transitive. Then symmetry, anti-symmetry, sometimes you have to see a bit. Okay. Then second one, if we let X equals to 2, Y is equals to 4, then I know that 4 is equals to 2 times 2. This implies that 2, 4 is an element in R. However, because we want to prove symmetric, means that I want 4, 2 is in R as well. But if in this case here, we will have 2 is equals to half times 4. And half is not an element, it's not an integers, right? Therefore, R is not symmetric. Since R is not symmetric, then we can immediately conclude that R is not equivalence relations. Okay, so no. Then the next is R a partial order? Of course, then we test on anti-symmetric. So for X, positive integers, and Y, okay, positive integers, we can write X is equals to C1Y and Y is equals to C2X. Then we sub this Y equals to C2X in to the first equation here. We have X is equals to C1, C2X. Since X, they are positive integers, we can just divide to get C1, C2 is equals to 1. And then we also know that, yeah, that's why sometimes in here it's important to write that because set of positive integers, so our C1, C2 must be positive, right? Since positive, we conclude that C1 must be equals to C2 must be equals to 1, right? Then if you sub C1, C2 insert back, then you will get X is equals to Y. Yes, so in this case, we know that R is anti-symmetric. Lastly, R is transitive, right? Then for X is X, Y, Z, set of positive integers, then we can write Y is equals to XC1 and Z is equals to YC2. Okay, remember, positive. Then we put Z is equals to X, C1, C2. This concludes that X, Z is an element in R. Therefore, we know that R is a partial order. With this, we have come to the end for the tutorial on relation. As this is my first time doing a video recording, so I'm kind of nervous. And if my pronunciation is unclear for some point, please forgive me. Thank you.